start with a short video that some of our students created a couple of years back.
My name is Chris, and I'm in computer science.
My name is Amanda, and I'm in computer science.
I'm Curtis. I'm doing a degree in computer science.
I can work in web design, computer programming, robotics.
I'm specifically interested in gaming because I like the idea that I can graduate in computer science, go in, develop video games, and then I'm basically working on something that's going to affect a mass audience or be entertainment for a mass audience.
I'm interested in biomedical computing, which also lets me work in a range of other subjects such as biology and medicine, which all relate directly to computer science.
For me, computer science is great because it can be both technical and creative. Once I graduate, there are a lot of different job opportunities in many different fields.
Telecommunications, graphics, networking, software design.
Computer science is not just about working in programming and algorithms.
You can focus on exactly what you want to focus on. Computer science is literally the future of technology.
It's awesome. It's exactly what I want to do.
And over the last 10 years, we have progressed, and we are actually the first department within Lassonde School of Engineering that is offering the first engineering program, well, actually the first enhanced engineering program. We did have a few programs in between that we started like 6-7 years back, but electrical engineering will be the full program that will be offered by under Lassonde School of Engineering by the department. And today actually is the 5th day since the time we changed the name of a department from Department of Computer Science to Department of Electrical Engineering and Computer Science. Now, coming to my presentation, essentially the topic that I'm going to talk about is signal processing. And what I hope to do in the next 45 minutes or so is to give you an overview of signal processing, some of the research applications that I have been lucky to be involved with in the last 20-25 years, and essentially also give you a brief insight in terms of where signal processing is leading in the coming years. So no matter which electrical device you have picked, even mechanical devices that you have picked, signal processing is the heart of it, right? So here what I've done is I've illustrated a simple example of your cell phone. So what you do, you're probably, those of you who are not technological savvy, what you can see that you have the speaker, you have a person who is speaking, essentially a voice signal, and you have someone receiving the signal at the other end, and hearing the speech at the other end. And there's a lot of processing that happens in between. So first of all, the voice signal is converted into an electrical signal through a transducer. That's, if you have a cell phone, the transducer is built inside it. And then there is a central processing unit that converts this electrical signal into another form of signal that can be transmitted over the air. So the signal that you see on the extreme right-hand side, that is actually the signal that you transmit, right? This is called a modulated signal. So you can see there are 3 blocks or 3 systems in there, and I would try to explain this in more detail in the next slide. But essentially, the voice signal is converted into a signal that can be transmitted, communicated to the base station using microwave. Now, once this electromagnetic signal is received by the receiving cell phone, it's again converted back into the electrical signal, then using the transducer to speech signal, which you can hear. So, a very simple example of a cell phone, and we use it very frequently, but just to give you an idea of what kind of signal processing is involved in a cell phone, this should actually give you an overview of what kind of processing is involved in a cell phone. And actually, the 4th year course that I teach for our electrical and computer engineering students, it goes through each of these blocks. Okay, and just to briefly, highlight some of the stuff that goes on in here, we have an information source, which essentially is you. You say, you emit or you say the speech signal. The speech signal has to go through all the steps. So the first step in here, for example, is source encoding. So what do we mean by source encoding? By source encoding, essentially, what we try to do is we try to compress the speech signal. If we try to transmit the speech signal in the raw format, then essentially, it's a lot of bandwidth that is required. So you try to compress it, followed by encryption. In certain applications, it's important for you for the information-bearing signal to essentially to have some protection, so that if someone else acquires it, they are not able to extract meaning out of it. And then there are a number of steps like channel coding, multiplexing. Multiplexing is an important step because the same communication link, which in this particular case is air, is being used by a number of cell phones. So how do you combine all these signals so the same channel or the same communication link could be used, and essentially, but at the same time, only one combined or one accumulated signal is transmitted. Then the other steps like bandpass modulation, frequency spectrum, that I won't go into the details. But essentially, whatever you do at the transmitting end, you perform the reverse step on the receiving end. So the idea of this slide was not essentially to go into all the details, but to tell you basically that even for something like a cell phone and even for cellular communication, there's a lot of processing that happens at the back end that is almost transparent for you guys. Now, in terms of some of the fields of signal processing, and this is where I would like to spend some more time. These are some areas, and I'll go through them, through each of them one by one. But this is not an exhaustive list. In fact, if I try to do an exhaustive list, I'll probably spend many more slides for that. But let's go through each of them, and then I have specific examples for some of the ones that I'm involved with. Array processing. Now, if you go to the hospital, typically you will see ultrasound, MRIs, and also in, for military applications like radars and sonars. The field of signal processing that is involved in here is called array processing. And essentially what happens in this particular case, you see a device, and the device is connected to and either an ultrasound or an MRI is recorded. But in terms of signal processing, you have what happens is that you have a set of transducers, set of emitters. They emit an electronic signal. The reflection from your body is recorded by them, and that leads to MRIs. Another field of signal processing that you're familiar with is audio signal processing. Most of you have seen MP3 players at some stage or the other. So audio signal processing is another field of signal processing, but in this particular case, the application is different. You want to compress your music, right? So you want to compress your music in as much reduced form as possible. And MP3 is an example of it. And essentially what happens in audio signal processing is that you must have heard of this, this story in school days that, that essentially if you have a whistle that emits signal in the frequency range of 10 to 16 kilohertz, a dog, for example, can hear that signal, and essentially as the story goes is if you blow the whistle, which emits signals in the range of 10 to 16 kilohertz, humans don't hear them, but dogs have more sensitive ear. They hear them, and they essentially come back to the owner. So audio signal processing essentially makes use of audio capabilities of the human ear and of the human auditory system, and essentially all frequencies in the range which cannot be perceived by the human ear are eliminated, and that's how you get compression. Big data is another big problem nowadays in which signal processing professionals are involved. With the advent of computer and cheap disks, essentially what is happening now is that you have enormous amount of data. So for example, we are working with the bank, and for each client, they have got they have terabytes of data. And the bank really doesn't know what to do with it, right? So they're providing us this data, and it's like, is there some way that we can extract information out of this big data? And this is just not related to banks. If you look at newspapers, right? Newspapers have gone into the digital format now. And now in the digital format, these newspapers have terabytes of data again. Now, how do we extract information out of it? So that's essentially another branch of signal processing called data mining. Filtering, right? The application that I've written is noise cancellation, right? So in this particular case, to give you a simple example, I'm speaking to you, but in the background, you will hear a lot of other noises, right? For example, you can hear this humming noise coming from the speakers, or someone right next to you is talking to his friend, to his or her friend. Now, filtering essentially is a mechanism which allows you to separate the information-bearing signal from the noise signal. So a noise cancellation is an example of it. Genomic signal processing, this is something that I'll be talking about more in details, but the human genome, as you know, back in 1999, 2000, the entire human genome was sequenced. Now, that is about 1 billion nucleotides. So 1 billion, when I mean a nucleotide, essentially I mean a variable that can take 4 values, A, T, C, G. Those of you are familiar with genomes. So we have got 1 billion nucleotides human genome. Is there a way that we can extract information out of it? Not only extract information out of it, but use that information in a meaningful way. So that focuses on genomic signal processing. Image processing. All of you have used digital cameras and imaging systems, right? So we are talking of more complicated problems now. We are talking of video camera network surveillance systems, right? So essentially, like what happened, the tragic incident that happened in Boston, you know, we had a network of cameras which were from which videos were available, but it took the American intelligence companies a couple of days essentially to extract the right information. So what can you do? Image processing and video processing essentially deals with, if you have a network of cameras, is there a way that you can track a particular individual? Is there a way that you can get meaningful information out of that? Seismic signal processing related to earthquake, speech signal processing. You know, the application that I have is voice recognition, right? So we're looking at systems where you can essentially talk to your devices at home. You're sitting in the car and you say, you know, for example, turn on radio or dial this particular number, right? So it's not only that the device has to record the speech signal, but has to extract information out of it in a way which makes sense. So there is also the involvement of artificial intelligence in there. Statistical signal processing is another area similar to filtering, where you are essentially interested in analyzing and extracting information from noise-corrupted signals. And finally, the last example that I have is in here is video processing, right? Again, you get all these videos at home, right? Back when I was growing up, it sounds like ages now, but when I was growing up, essentially we used to receive one channel at home, right? And now you can receive hundreds and thousands of channels either through the cable or through the microwave link. You know, if you have a dish, it's essentially coming through microwave. So how has that been made possible? And essentially video processing is the field behind that. So I just wanted to give you a flavor of different fields of signal processing, but I'll go into more concrete examples now. So this is one particular project that we are involved with. There was a satellite called Topex Poseidon. It was launched from John Stennis Space Center. And it was a joint American and French expedition. And so essentially, this satellite had remarkable accuracy in terms of recording, recording images of the Earth. So this is the original image that was given to us, but this is what the satellite recorded, right? And the number that you see at the top is essentially the signal-to-noise ratio. So we could determine that quantitatively. Now, the current state of our techniques, like the medium filters and the Wiener filters, they would process this received image and try to eliminate noise out of this. And you can see that the results are better than the received signal, but they're still not very close to the original, right? So in our signal processing communications lab at York University, we come up with a new patent. It's called the Gauss-Markov random process-based image processing, and you can see that the resolution is far better. For example, if you see these edges in here, you can see these edges more precisely, and we're still working on this to get a better representation, of the original. But this kind of processing is called image enhancement. You have a noisy signal recorded from some device, and essentially you try to extract the original image out of it. Now, this has a lot of medical applications. Those of you who have seen MRIs and those of you who have seen ultrasounds, they will see it's very blur, right? So what can we do? How can we enhance the quality of image recorded from those medical devices? So there's a hell lot of research that is going on in this area. Okay, so for the next, I actually have to explain to you the concept of okay, to explain to you the concept of video compression, I have to essentially show you this video. This is the video which was recorded at Shanley Park behind Carnegie Mellon University. So, this is a test video which is now being used more or less as a standard video in testing the algorithm, in testing video compression algorithm. But just to give you an idea once again, you can see it's about 10 seconds video, and at 30 frames per second. So we are talking a lot of data in here. So one way by which we can actually achieve compression when we are transmitting video is essentially to mosaic all the frames in that video in a still image. So the 10 seconds video that I showed you previously, the entire information in that video is represented by this single still image. And rather than transmitting the video, what we can do is we can transmit this still image to the receiving end. And then the next step really is just to send the coordinates of the various frames, and you extract the frames out of it. So we are talking of compressions in the order of thousands of values if such a representation is done. The other video compression techniques that are now used, they're essentially wavelet based and JPEG based, but this more or less illustrate the idea in terms of video compression. Another application of image processing that I have been involved with is genomic signal processing. So those of you who are familiar with DNAs, essentially the DNA consists of a string of nucleotides, and there are 4 such nucleotides. So if you see through this, you'll see there are 4 nucleotides A, T, C, G. So the entire human genome is represented through these 4 nucleotides, or 4 alphabets, as sometimes scientists call them, and they essentially occur in pairs of strands, right? And there's also a unique feature in here that A only combines with T and C combines with G. So essentially, if you have one strand, that is a unique representation because you can get the second strand out of it. Now, it is remarkable that if you look at these nucleotides, and if you compare the nucleotides across various mammals, for example, it is remarkable how similar they are. And as a matter of fact, what scientists, and I'm not a biologist, but if you talk to a biologist, he or she would essentially tell you that 99% of the human nucleotide is essentially what they call junk DNA. It serves no purpose. It's only 1% of the nucleotides that serve the purpose. That is useful, right? And so here, for example, if you compare the whale and human nucleotides, you can see there's a lot of similarity, and there are only 4 nucleotides in here that are different, right? And it's incredible that if we assume that DNA is essentially the building block, these differences result in different mammals, right? And that is true for a lot of other mammals. But But a basic problem in signal processing essentially is, how do you identify which region among the human nucleotide is useful and which region is not useful? The region that is useful is essentially called protein coding region. So the yellow region that is shown in here is called protein coding region. And the region that has not been highlighted is essentially junk DNA or non-coding region. Now, how can you do it using a computer? If you ask a biology, he would essentially take it to a wet lab, perform, maybe now it happens in weeks, but initially it used to take months for them to get or to determine the coding regions. Now, the genomic signal processing is a field that allows you to essentially to identify, in this particular case, the protein coding region from the non-coding region. So here is a technique that we have developed locally here at York University, and you essentially do frequency transformations and then do some filtering on it. But here is the result, and this is a human genome about 8,000 nucleotides long. The biologists essentially told us where the protein coding region are. We process this data, and if you look at the peaks, these peaks correspond precisely to the coding regions. Okay, and I can essentially run this in a few seconds now, right? There's a lot of mathematics behind it that I'm not showing you today. In fact, in all signal processing, if you want to be involved in signal processing, one main thing that you need to know is mathematics. So there's a lot of mathematics behind it that's not being shown in here. But you can, if you give me a human genome or part of a human genome and ask me to tell you where precisely the coding regions are, I can run this algorithm and I can tell you that. So that's what genomic signal processing is. But genomic signal processing is not just limited in here. People are looking at other kind of research projects. So, for example, one research project in which one of my colleagues within my lab is involved in is detection of HIV, detection of HIV DNA from the human genome. Now, the HIV is essentially a retrovirus. What that means is that, when an HIV virus infects the human body, its DNA becomes encapsulated within the human DNA. Right? And that's the reason why it's so difficult to cure, because the retrovirus DNA is part of the human DNA, and the first thing you really have to do is you have to identify where the retrovirus DNA has inserted itself. So they are essentially looking at genomic signal processing techniques where the retroviruses could be identified from the human genome. So that will be the first step which we believe will lead to the cure. Another area of signal processing that I referred to was array processing. And array processing is essentially present not only in military devices, but is also present in medical devices, ultrasound, MRIs. So I mentioned it very briefly, but let me go into more details now. In any medical device or any military device, the idea is that you want to locate, I'm calling a scatterer in here as a generic term, but essentially in medical devices, this could be a tumor. So, and this could be a human body. So this is essentially a medium, and you are interested in determining if a tumor is present, and if a tumor is present, what is its location. Now, what you essentially do is you have a set of array elements. We call them antennas, and these are located outside the body. And these array elements, they emit a probing signal. They probe the human body by emitting a weak signal. Now, these scatterers, if you look at the tumor and compare it with the normal human cells, the tumor behaves differently from a normal human cell. As a matter of fact, the tumor reflects the signal strongly, whereas a normal human cell would allow 90 to 95% of the signal to propagate through. And these reflections from the scatterer or from the tumors are then recorded by the array elements again. And essentially, the array elements use these reflections to determine whether a tumor is present, and also if a tumor is also in identifying in localizing the position of the tumor. So to give you an idea, I have a very simple illustration in here. Suppose this target is essentially your tumor, right? And essentially what I do is, one of these, and this is my antenna array that is I'm using for probing. Let's assume this antenna array has transmitted a signal, and that signal got reflected from the target. So this signal got reflected on the target, and this is what the array is recording. And in this particular case, I call it using psi. Now, interestingly, what we have discovered is that if we time reverse the signal, and essentially what does time reverse mean? If you look at the waveforms, and you will be able to determine what time reversal means. Essentially what it means is that the signal that you have received last, you transmit it first, and the signal you have received first, you transmit it last. So you essentially, it's like playing a video movie in the opposite direction, you know, in the reverse order, like playing the reverse button on your DVD players. Now, if you time reverse this, so once again, if you time reverse it and transmit it back into the medium, a very interesting phenomena occurs, and that phenomena is that the time reverse waveforms, they actually focus at the location of the tumor, right? And we were the first ones, you know, our lab were the first one to prove this analytically using mathematics. That, you know, why does, we call this super resolution focusing. Why does this super resolution focusing occur? Okay? But essentially, from a radiotherapy perspective, this has huge applications, right? We were talking to radiologists at South Lake Hospital in Newmarket, and they essentially told us that when they are trying to eradicate a tumor through radiotherapy, roughly 40 to 45% of normal tissues around the tumor are in fact affected, are in fact damaged. So if we can have this kind of super resolution focusing, that will allow us to eradicate tumor without affecting the healthy tissues. So we essentially ran a simulation, and this is a simulation which is based on an MRI, on a set of MRIs that we obtained from South Lake Hospital. From those MRIs, so this is essentially an infected patient. From those MRIs, we developed the electromagnetic properties of the human breast in this particular case. And we applied this phenomenon of time reversal to it. So in this particular case, the black region in here, there are two different simulations we ran based on different cross sections. The black region that you have in there is essentially the human chest. The skin is shown by this firm line. And the pluses that you see at the top in there are essentially the array elements. And this is another cross-section of the same thing. So what we do in this particular case is since assuming that we know the exact location of the tumor, we place a weak source in there. This weak source emits a signal. This signal is recorded by the set of antenna elements. The antenna elements time reverses them and retransmit them back into the medium. And we compare, you know, how much healthy cells are affected and compare it with the current state of our techniques. So here are the two results. Let me just focus on the one on the left-hand side. And now this is essentially what we are doing in here is we are plotting the temperature profile for the region around which radiotherapy has taken place. Now the temperature profile is gives you a good estimate of how the healthy cells are actually getting affected. So the outermost contour in here in the temperature profile, it corresponds to 37 degrees Celsius. And as you go inwards, then the next one is 39, and then 41, and so on and so forth. Now the top one is essentially based on our technique that we have developed, based on time reversal. And the bottom one is the current state of art that they use in the hospitals. And you can see if you compare the two, there's almost a 50% reduction in terms of the effect on the healthy cells. You can see the contour for 37 degrees Celsius has got much larger area in the lower plot. And the same thing applies in here for the other cross section. Again, you can see that the area enclosed with the current state-of-art techniques that are used in radiotherapy, the area enclosed is much higher as compared to the top plot in here. So here I made a big assumption. I said, okay, I know the location of the tumor. And actually what we have done is we have developed techniques that allows us to determine, to localize the tumor as well. So this is again an example. This is an MRI of a patient that was made available to us. We extracted the electromagnetic properties of this human breast and ran an electromagnetic simulation based on time reversal. Those of you who are familiar with physics, whenever you're running electromagnetic simulation, we're talking of Maxwell equations. So there's a lot of mathematics behind this. But again, I'm just giving you the results. So here are a couple of results that I have. The one at the top is essentially what is developed by GE, right? This dot in here is the exact location of the tumor that was diagnosed by the radiologist. And this triangle, if they run their computational technique, the triangle essentially tells you what the location of the tumor is. You can see this is the skin, and this is, and the line at the back is essentially the human chest. We ran the time reversal based localization technique, and you can see that the location of the estimated location of the tumor is close to its true location. Not only that, but you can see there are more details available in here that you get with time reverse, and some of these corresponds to blood vessels. Here are also, we also did a comparison with some other work being done at other universities. Johns Hopkins University and at Berkeley. So here are two of those results, and this is the result that we have obtained from the signal processing lab. In this particular case, what we do is we have two center of antenna arrays. One array is transmitting the signal, the other one is reversing the signal, the other one is receiving the signal, then we time reverse it, retransmit it back, and the first one records it again. So again, you can see that the quality of estimation is much close to actual reality with our technique. This was as far as time reversal signal processing is concerned. Let me go into one other application. The ground penetrating radar application, where time reversal is used, where time reversal and signal processing is used quite a lot. Now, what is a ground penetrating radar? A ground penetrating radar is essentially used to determine underground objects. So a typical application of a ground penetrating radar would be detection of landmines, right? So here is, for example, the simulation that I'm showing you. Again, we have done it within our lab. The top dark blue region is actually air, and you would essentially have the ground penetrating radar or the antenna array located in here. The blue region is essentially the top surface of the soil, and the brown region is the bottom surface. And you can see it's not only different in terms of colors, but it's also different in terms of the permeability and conductivity of the soil. Now these rectangles that you have in here are essentially objects, which for us are essentially noise. The circular object in here is essentially a landmine. And what we are interested in detecting the location of the landmine without digging into the soil, but essentially using the ground penetrating radar at the top, right? And again, we ran various simulations based on Maxwell equations for ground penetrating radar, just to give you an idea of how electromagnetic waves propagate through the soil. The ground penetrating radar is actually located in the center of this this blue region that you have in here, and over time, this is how the electromagnetic wave propagates into the medium. The reflections of these electromagnetic waves are recorded by the ground penetrating radar. And here are actually some of the results, right? For ground penetrating. Now let me tell you what these graphs mean. Along the y-axis, essentially what I am plotting is the error, right? It's been plotted in a scale called decibels. And on the x-axis, I have signal-to-noise ratio. So here, on the extreme right, the signal-to-noise ratio is higher, so signal value is higher, noise is small. On the left-hand side, the signal value is low and noise is large. And you can see, first thing that you can see is in all these 4 plots that as the signal-to-noise ratio decreases, the error also increases. Signal-to-noise ratio decreases, error increases, which intuitively makes sense. If the signal value is small, the error should be higher. Now, the blue and the green dots that I have in here, the blue dot is essentially the error in terms of localizing, in terms of determining the location of the landmine based on some of the current state-of-art techniques, and the green one is based on time reversal. Now, when we actually tested this and we showed it to a defense company, they came back to us and they said, okay, well, we believe that your technique is performing better, but can you give us a concrete proof that your technique is actually better than the one with whom you are comparing with? So for such cases, what you typically do is you plot what is called performance bounds. And what are performance bounds? These lines in here at the bottom, the straight lines are performance bounds. So performance bounds essentially in this particular case, these are lower performance bounds. So the lower performance bounds essentially tell you what is the best that you can do using a particular scheme, okay? So if I use the traditional techniques, the conventional techniques, this is the best I can do in terms of the error. So I can reduce the error up to this particular level, right? The techniques that we have developed here at York are essentially shown by this green plot in here, a different signal-to-noise ratio. And you can see that there is a significant difference between this. So it's not only that our schemes are performing better, but the main point that should be stressed in here is that they also have a potential of performing better if we come up with the ideal setup. Okay? So essentially, these were some of the signal processing applications that I wanted to discuss with you today. I leave you with another video, which again was developed by one of our students. It's essentially a rap.
Take off them specs to show that you're ready. Make the world go round and we be keeping it steady. Show your true skills, the real colors involved. Engineer, laboratory, show we've evolved. Just don't stop when you've been taught one thing. Learn the whole park and expand like a germ ring of science. Defiance, don't listen to the alliance. I'm sitting here repping with the Pentium dual appliance. Listen close as I tell you, yo, about computer science and its whole new role. Taught one thing, then many more. Trust me, this job is not a bore. Many different categories to choose from. Video, media, film is what I've done. Never think less cause you're using your mind. Students like us can grow and climb. Don't get us wrong, don't get us wrong. 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 We're not nerds and we're not alone. We're not social outcasts and we have cell phones. We like technology and don't like it slow. We can have a conversation about Windows. I got broadband, turn up the Wikipedia 00101, delete ya, click, drag, drop, zoom, print, scan, fax. Technologic version of the world, just relax. We're all the same, I love my science. Bill Gates and Steve Jobs are in compliance. Make a big dough, yo, don't forget about the checks in the mail, big money, yup. One last thing before I leave, it's a myth, I'll bust with my science sleeves. Listen real close and let's hear you say, what's computer science? Well, press replay.
So these videos are essentially part of the outreach activities that we are involved with high school. And the idea really is to get high school students involved in computer science and engineering at a younger age. So we essentially go to these high schools, make this presentation, and show these videos to them, especially to grade 8, grade 9 students, before they have made up their mind in terms of selecting one of the area. And one of the problems that we are seeing in essentially in technical area is that there are not many Caucasians, not many white Canadians that are coming into technical field. A lot of immigrants are moving into this area. There are a lot few females in this area, as you may have noticed. So essentially that brings me to the end of my presentation. This is my email address and this is the web link.